Next, I'd like to introduce Francois Marcotte, who will be presenting Navigating High-Speed Transceiver Challenges, Evolutions, Impairments, and Dispersion. Francois is a senior member of the technical staff at EXFO and traveled from Laval, Quebec today to join us. This is Francois's first time presenting at NANOG, and it's a pleasure to have him here. Welcome, Francois.
Thank you. Thank you very much. I'm from Montreal, so you know. So I have this strange accent. So I'll use this little guy here to switch my slides, and we start. Actually, I'll talk about transceivers quite a lot. There's a little bit technical, but I'll try to keep it smooth, especially after lunch, you know, and there was no coffee. So, let's go. Let's look at the evolution of transceivers over the years. When I started back, actually, GBICs were the one available. You know, back then it was not Ethernet at all. It was SONET. If you were familiar with transport, it was SONET transmission or SONET transport, we call it, and it was using GBICs. After that came the SFP quite later in 2000. The SFP was made for 1 GeV, but also for SONET OC48 and OC12, if you were familiar again with that. ZenPack I never saw, X2 never either, myself. XFP, yes. XFP were, you know, they were famous for 10 GeV when it came out. It disappeared, replaced by SFP Plus, because the SFP Plus was the same form factor as the SFP for GeV. And people decided to remanage their host to be the same cage. And the SFP for, you know, cost saving, heat dissipation, and all that stuff was perfect. So that's why you still see today SFP, the most popular interface, all the way up to 28 now, because you can have SFP 28 gig. QSFP, the most used for high speed after 40 gig. Used also for OTN, if you are familiar with that transport technology. But Ethernet is using it all the way to 100 gig. Then came the QSFP 28 type, 100 gig, and QSFP DD for 400 gig. And then today, if you're looking at 800 gig, I'm not talking too much about 800 gig today, but we can talk about it if you have questions. OSFP is really the form factor to go forward with 800 gig and 1.6 terabit per second. Because of the size, they can fit inside some multiplexers and modulators like 16 QAM, 64 QAM modulation, if you know what I'm talking about. But I'll try to explain the most as I can. So the most used today is SFP Plus all the way to QSFP DD. Those are the ones. So QSFP form factor and SFP form factor are the one used in the market. Let's talk about a little bit technology. NRZ, non-return to zero. This is the basic of all communication. You're sending zeros and ones. And the principle here is when you send a 1, it stays there until you have a 0. So they are reducing the voltage. Basically, when you are modulating the signal, you are putting a voltage or a 0. That was changing with PAM, which I'll talk about. But this is actually one symbol. We call it PAM 2. So they're actually 0 or 1. So there's always one symbol, which is sent. Whoops. Yeah. So the PAM4, which is pulse amplitude modulation, 4 levels. There's actually 4 levels of bits with a binary of 2 bits per symbol. So 0, 0, 0, 1, 1, 0, and 1, 1. Every one of them has a specific voltage. So in the transceiver, when it reads something like this, it has to be at that certain voltage, like 0, 2.3, 3.3, and 4.5. And then if they are not exactly at that kind of level, you have bit errors. Okay, so this is quite important. So understanding the noise can create a lot of issues. If you look at the eye diagram, an eye diagram is a look with an oscilloscope to the levels all these levels superposed to each other. So you see the levels at the bottom, 0, 0, 0, 1, etc., and 1, 0, and 1, 1. So you know how much density of 1, 1 you're getting and how much uncertainty you're getting. And as the eye is closing, the most probable errors would be happening. You know, when you are manufacturing transceiver, you need to do an eye analysis to make sure that the eye opening is wide enough so you have very good performance. So if you're buying a 400 gig transceiver today, you'll pay a prime dollar of, let's say, $20,000. You say, whoa, that's expensive. Yeah, it can be expensive, but then they are guaranteeing that it will not fail, and if it fails, they will replace it for free. Now, you can buy another 400 gig at $2,000. Now, what's the difference? So we'll talk about that during this presentation. Why one transceiver is way more expensive than another one. And if you have questions, let me know. So that means that signal-to-noise ratio is critical for something using PAM4. You're dividing by 3. If you're comparing with an NRZ type signal, there was only one signal-to-noise ratio, so bottom voltage, top voltage, and now you have 3 levels, so you are basically having 3 zones of signal-to-noise ratio. So the signal-to-noise ratio is divided by 3, basically. So can you go as far as a regular transceiver using NRZ? No, it's not possible. So what they did to the technology, they add FEC, which is forward error correction. So it's inside the transceiver. That mechanism is capable to correct the bit errors as they are happening. So actually, not at the transmitter level, but at the receiver level. The receiver is seeing that there's bit errors happening and then will autocorrect the errors. Actually, the FEC is taking extra space of data bandwidth to transmit redundant information on the bit stream. And if that information is, it's parity measurements, by the way, Reed-Solomon, which I'm not getting too much in the details, but if you want, I can provide you with the full guide and a full application note on this. But what it is the FEC is mandatory for 400 gig. And now they're seeing the advantage of FEC because it's autocorrecting and it's adding 7 dB of signal-to-noise ratio resist or capacity. So meaning you can go 7 dB more distance in optical fiber, which is quite a lot of distance, like 20, 30 kilometers further down. So PAM4 now is becoming popular for 100 gig. So you will see also, or you can already see a 100 gig transceiver with PAM4 available. So those are the most advanced high speed you can find out there. Those are the CFP. The CFP is a bigger one. It came out in CFP2 at 100 gig at the beginning, really at the beginning of 100 gig 10 years ago. CFP2 was invented. Why it's still in use is because in Asia, they are using it like all over the place. They were the first to introduce FEC for submarine system because you don't want to go and correct these or add amplifiers. So you want to have minimal amplifiers across the sea. So for maintenance and operation, it's a lot more convenient. You don't have to go with a boat and change, let's say, an amplifier once in a while. You're trying to limit that as much as possible. So CFP also is a bigger one form factor, giving a lot of room for electronics inside. Now, is it popular in America? No. I don't see any CFP people, using CFP. If you are using CFP, then fine, but you're very few people using CFP in America. QSFP, of course, that's all over the place. An SFP. That's why QSFP is a middle range. You can go all the way to 800 gig. The newest one is called QSFP 112. I'll explain what this is. When you buy one today at 400 gig, it's called QSFP DD. But in fact, the real name is QSFP 56 gigabaud 400 gig. So, or DD, dual density. Then you have also a lot of DACs direct access cables. You have also AEC electric assembly cables, and you have also optical assembly cable. Those are fantastic for data centers, interconnection between servers, between a server and a router. All those are quite cool. They don't need any cleaning, because when you deal with, fiber optics, you need to clean the connectors. And if it's an MPO, which is a multi-core connector, where you see on a connector there's like 12 different fibers, with 12 core to be clean. So you're cleaning one core, the dust goes to the other one, then you clean again, it goes to the third one, and then you clean again, it goes to the last one. You clean again, it goes back to the first one. So I don't know if you've been dealing with MPO connectors. They are a pain. And cleaning, you're trying not to do, if you can not do cleanings on the MPO is the best. But there are, clippers and clickers. You can put alcohol on the clickers and then you will actually clean it. But as the alcohol dries, then the dust comes back in the middle, by the way. So you need to use also a dry cleaner after using alcohol. Just a side note. So breakouts also very cool. So let's say you have a 400 gig device and you want to distribute that to 4 times 100 gig switch. It's perfect. You have a breakout system, so you break the 400 gig to 4 independent 100 gig, and you can test that easily with the BERT tester that exists in the market. And this is quite cool because you can segment your traffic and capacity. So it's a good introduction to 400 gig. Instead of changing everything to 400 gig, you just put this in, and then with the breakouts, you have flexibility. There's other kind of breakouts like 2 by 200 also available. And you can also now buy the 4 by 400, but that's 1.6 tera. But still in a lab. It's not available yet on the market. So the difference between, if you look at the QSFP, the way it's made, I'm taking a QSFP, but it could have been an OSFP or SFP. You have an electrical side and you have an optical side. The electrical side has multiple lanes, electrical lanes we call. In this case, I named them 8 by 25, 16 by 53, and 8 by 100. In fact, I'm including here transmit and receive. In fact, the transmitter is using 4 by 25, and so is the receive. Same thing for the other ones. So that electrical side is quite the challenge for switch manufacturers. Or if you're developing, let's say, a router or a switch out of a server, so a virtual router, for example, and you want to use these type of transceiver, you have to make sure your OS is capable to support that kind of, for example, the QSFP-DD LR8 in the middle. Then this one has 53 gigabit per second lanes. So your equipment should be able to handle that kind of bit rate on every single lanes. If it's not, then you need to correct, obviously, your host before using that kind of transceiver. Now, this year, we're moving to QSFP 112. So meaning that there's 112 bit per second capacity on the electrical lanes, and you have up to 8 of them. The beauty of this, going with QSFP 112, is you have less heat and power consumption coming from the QSFP-DD, because there's already the 8 lanes. Let's say you're going on the LR4, so you just need a MUX, a simple MUX that will MUX those 4 100 gig lanes into 2 400 gig, or 2 100 gig. You have 2 of them, then you have your 400 gig output. So that's quite interesting. So for lowering the cost and lowering the heat consumption and power consumption, yeah. Now, if you look at it from a point of view outside, so multiplexing is adding watts and heat, obviously. Every time you have a MUX inside, can be electrical MUX or optical MUX, you're adding, of course, a need for electricity and power. And it's, of course, dissipating heat. So this guy or this type of a transceiver can eat like a toaster. especially at 400 gig. The first version, they were using 28 watts. They were quite hot and could burn, for example, your host. For example, at Expo, we are developing test equipment to test the transmission rate and all that stuff. But we are also validating transceivers. So when we did try the new 400 gig because there's so many manufacturers, then we had an issue with heat. So we had to redesign the cage where the heat is dissipated correctly. The airflow is sometimes also different. You can have a transceiver with the fins like they are parallel to your transceiver, where some others are like a stars type of dissipation diagram or design, sorry. And then it dissipates the heat in multiple directions. It was decided for 400 gig and 800 gig to be linear fans to dissipate the heat. So when you are dealing with this kind of transceiver, you have to make sure your equipment can support it, but can support the heat. If you look inside, it's pretty cool. This is what's really inside. It's a nice picture, in fact. I don't remember where I found it, but if you look, there's modulators. There's modulators inside. In this one, it's a FR4. So there's different acronyms, and I'll talk about that later, but LR4 long reach, FR front reach 4 lambdas, FR4. So there's 4 lasers inside. There's an optical mux, but there's also an electrical mux, which I'm not showing because the lanes here, it's 8 by 50. So 4 transmitter, 4 receiver. And then you have also the laser, which is not far away from the mux and the modulator. What's happening is the mux can eat up the laser, creating noise over the laser. So you need to put some isolation. I'll talk about that too. And also you see there's a spool of fiber inside. It's because if there's this is just because you don't want to launch directly to the ferrule. You know, on an optical, you have a ferrule. This is like a mirror. So the laser will hit the ferrule and then gets to the other side of the connector. But that ferrule is like a mirror. So the laser, so that will reflect laser back to the source and create some noise. So that's why there's extra fiber inside to lower down a little bit the launch power, we call it. Now, let's look at different 100 gig transceivers. Different, version for different purpose, like 1 meter, 3 meters, those are the assembly cables. You decided to be using electrical or optical. If you're using electrical, it can be passive. So that way, you're not using any electricity. You're saving a lot of, over thousands of connections, you can save quite a lot. I did try, recently DAC. It was 800 gig to 800 gig. But one side was passive and the other one was active. So you're using half of the power. So there's all kind of different solution for different needs, but they're trying many things. You have also breakout 800 gig to 400 gig. The 400 gigs are passive and the 800 gig is active. Yeah, I saw that too, and we did try that a month ago. And it works. It's just distance is not very long. You have 3 meters maximum. Now, what's the purpose of this? Again, it's you have a big system server, 800 gig transceiver connected, and then you want to split that and go to your 2 existing 400 gig switch, and then it would work. And what I'm showing also on this is the media. So, for example, the SR4, short reach for lambdas. In fact, there's 4 fibers. In this case, it's 4 fibers. So 4 for transmission, 4 for receiving. So at least you have an MPO here that needs 8 core or 8 fibers inside. And that's what you see here, the magenta type color. Yeah. And then you have to clean those. When you look at the CWDM4 and PCM4 or FR1, DR1, so the first 2 are using single mode fiber MPO. So the MPO, again, is a multi-fiber core connector. That's interesting. They were the first to use single mode multi-core. And then you have the FR1, DR1 single LC connector. Some people, they prefer that, those LC, because it's only one connection. What's the advantage? What's the advantage of using, they are carrying the same capacity, 100 gig in all situation. One is using MPO, the other one is using LC. I have a preference for LC myself, but sometimes the price may matter, right? If you want to buy two, it's, who cares, you could buy LC. But if you have to buy 1,000 or 10,000, maybe the MPO will be cheaper a little bit. Why? Why the MPO is also something interesting? Because why is it cheaper? Anybody knows? Huh? Yeah, that's right. Who said that? Yes, that's right. No MUX. So there's direct fibers. But however, you have no MUX. So you're reducing the power consumption because MUX is taking a lot of power. But you have 4 lasers for every 4 fibers. And you have 4 photodiodes to detect the light. The trade-off of power is sufficient to reduce the cost. But then you may find those more expensive. You say, why? Because they would put inside more expensive lasers with higher stability. Then you want to go probably further. Like you have a difference between 500 meters and 2 kilometers. That's why you pay a little bit more. Stay the same configuration. You don't want to change, let's say, your patch panel and all that. So you'll go with, for example, that higher power MPO. That's about it. The rest is pretty much the same. The ZR4 just go further down. LR4, very popular for transport. But again, every time you're using those, you need to go to a transport element. The transport equipment, we call, or the switch, will need to convert those lambdas, 4 fibers, whatever, into a single channel. And usually it's coherent optics, which I'll talk about. The next one is pretty much the same. I won't go through much in the details, but this is about 400 gig. It's just different features, LR4, LR8, DR4, different distance, and so this is for reference, because since you're going to get the presentation, you can always look at it. But what I want to get to is to this. This is evolution. The top one is where you see inside the transceiver. I know it's really electronic diagram, but you have the substrate, which is a component. You have the ASIC, which is a programmable one, actually a chip that you can program your functions. You have a digital signal processor, which align, equalize, reduce, amplify the signal. Actually, you have 2 of them. And then you have the laser, which is in yellow, where you plug basically your fiber. And as you can see, the PCB, the first PCB, you have 2 DSPs. So it's consuming a lot more intelligence, versatile, but also more complex, so they are expensive. Recently, this year, we got co-packaged optics called CPO. And what they did is they put the laser next to the ASIC. They had to put, of course, next to it, and only one DSP. But the problem is the laser was burned by the ASIC and the DSP. So they had to keep, I think it was the minimum 5 millimeter distance between those things, so it doesn't burn. But fantastic device, the CPO. Co-package will become the future of computers. In fact, your chipset will have optics right next to it. So you'll buy an optics actually chip that will go inside your computer, and everything inside will be optics. That's where NVIDIA is focusing on, and some other companies looking at chipset. Intel, all these people are looking at CPO. LPO is a different story. LPO is the same thing. Again, you're reducing the DSP, but you're putting back the laser a little bit further away. So because of the, like I said, the heat and noise and everything. So you have a better linear signal, but you cannot go as far. But you're using TIAs, if you're familiar, transistance amplification. Yeah, TIAs, yes, sorry. And then those are having a great linearity on your signal. However, it can go as far. So 500 meters will be for LPO. LPO are just coming out now. I'm testing them with manufacturers. Okay, so what about now coherence? I talked about the transceiver, all that's pretty cool. We call that client side. So when you look at the card, when you see all these SFP connection and QSFP, this is a client. This is connecting to your switch, your router, your servers. And then they go to the transport Ethernet. Then they need to be converted into OTN, optical transport network. OTU4, maybe it resonates with you anyway. So the transport will encapsulate those Ethernet into a bigger container to transport over the fiber over long distance over DWDM. But before that, to be contained into a single carrier, to be able to be modulated at a specific wavelength on a DWDM, I know it's a lot of information. For example, you want to modulate it at 1552 nanometers. Then you need one single carrier. It cannot be a DR4, LR4. That is not possible. So they created what we call coherent optics. And coherent optics did exist a long time ago. They were invented before for long transmission over the submarine system. And they were called the coherent line cards or the OTN cards, where you have the line connection. In fact, it was coherent optics inside. Now, today, you can buy a coherent QSFP form factor transceivers. So it replaced completely the card. So instead of having a big chassis with these line cards, now you have one multi-connection client line together, and you can mix and match your transceivers. So you can have QSFP LR4 going to your interconnection, routers, switches. And then if you want to transport over another data center or CO, then you can use the coherent optics, and then you can tune it to the specific DWDM wavelength and put it inside that specific fiber, and that's it. So you're just eliminating a full type of, you're saving quite a lot of money. If you're deploying green zone, green data centers or CO, then you go with coherent optics. You're going to save a lot of money not using the transport, legacy transport. So all the manufacturers, Fujitsu, Lucent, not Lucent, but Sienna, Cisco, they all go with the coherent, Juniper as well, of course. So it brings into this concept of Constellation quadrature amplitude modulation, which is QAM, where you remember you had the two NRZ 0 and 1s, and then you had the PAM, which is 0, 0, 1, 1, etc. Now you have phase and amplitude shift. So you have in a zone, if you want to go 1, 0, 1, 0, so there's 4 bits per position. So then you have to put that specific bit at a specific amplitude with a specific phase, and this would be 1, 0, 1, 0. If you want to go with 0, 0, 0, that's 180-degree shift, same amplitude, or actually negative amplitude. So that's about QAM transmission. So when you look inside a transceiver, it looks like it's quite more complex. There's a polarization combiner now, which is added. There's a coherent mixer. You need a laser. The laser inside actually is at two purpose. It's uses for the transmission, but it's also used for the receiver as a reference, as the coherent system has to rephase the photons to split them back into individual carriers or streams. There's still a DSP inside, but this took 20 years of development to get there, to put that into a small form pluggable. So that was a challenge for the industry, for all these transceiver manufacturers. Any questions so far? I know I'm talking and, Okay, that's time. Okay, perfect. The laser, you're mentioning that it's used at the receiving end. Can you elaborate on that? I don't have a lot of time. I still have 15 minutes to go, but what I can do is I can add to the presentation or send to the people how it's really done, because it's like quite complex, and actually there's like also dual polarization happening inside. And dual polarization is light is polarized. And I'll go there, and that's a good thing actually you asked a question. For the next part is there's two polarization. You can look at it in two axes, like it's a sphere of light. It's a sphere, right? The light. So if you look at two axes, so this light can distort in two different directions. So that polarization can be used also for transmission. So in fact, when you are using dual polarization, you can then add more bits to the transmission. So having 4 bits. So in fact, one polarization deals with 2, and the other polarization deals with another 2. So it gives you so it gives you the 4 bits transmission. It's pretty cool. But like I said, it's complex, and I don't have the time today, but if you have my emails, I'm pretty sure. Yeah. You can send me your question. I'll be more than happy to send you more details on that, because it's quite a cool topic, and I don't have the time today. Thank you. Okay, so now going back to functionality, you need to know also CMIS. If you are dealing with the programmation of these switches or routers, for example, or you're making a new device, you need to know how to communicate with the transceiver. And CMIS, owned by OIF, Optical Internet Forum, they are now putting together a list of requirements when you are using a transceiver. And they are making all transceiver open, meaning that you can now use the Sienna transceiver into the Cisco world, Cisco transceiver into the Sienna, Juniper into etc. You see, it's a mix and match. We call it open architecture. And OIF is really focusing on that. So CMIS is about how you communicate with the module and what is the module capable of, and can you amplify the signal? Can you mux it to the specific lambda for DWDM? All that stuff is provided by the transceiver into the registry. So you have to read the registry, and you know all this. Now, another thing also you need to know is they are changing. Are you using different connectors? Is it LC? Is it MPO? The future one will have double capacity. So they will have actually 2 or 4 connectors, like duplex dual LC, dual MPO 12. I will not buy that, but that's just me. I'm not a fan of MPO, but I understand the principle. And I'm not talking about, it's not the expo mindset here, it's my own opinion. Okay. So what's happening in a transceiver and what can go wrong? So you have thermal noise, of course. That is creating random noise, random errors. You know, when you're doing a bit error rate test, what is random is bit errors are happening randomly. When they are synchronous, so they are happening at a very clocking time. So let's say every minute you have bit errors. It's due to an equipment. Something somewhere is not beating correctly. So it's not actually following the beat stream, so it's an element. But when it's random, it's usually optical issues. But in this case, I name, even if it's electronic, I name it as an optical device. So you can have random errors. So power fluctuation, random errors, laser quality. This is where you can pay much more for your transceiver, but then you're reducing quite a lot the error rate. And you have photodiodes, same thing for the receiver, yeah. You're reducing the errors, and that's it. So how do you test that? There's out there different things, but in my company, we develop a way to test very simply the transceiver. You just put the transceiver in, you put a cable between the transmitter and the receiver, you press a button, and it shows you power stability, laser stability, power consumption, temperature dissipation, all that stuff is in fact measured in a few minutes. So you know if that 400 gig is working, and you're not trashing that $2,000 transceiver because you believe, let's try another one. Because if it works, let's say you do this, and you think you fix the problem, it was actually a random error issue. It will eat up over time, and then after a week, you'll start having errors, bit errors. So that's a problem with that. So the last, so FEC, yeah, I talk about FEC and BRIRI because the time flies. So the FEC encoder is inside the transmitter, next to the transmitter and to the receiver. What it does, it adds redundancy to the communication, like I said before. So you can actually auto-correct, but up to a certain level. Otherwise, you have to double the transmit capacity to be able to correct everything, but you don't want to do that. Actually, you want to just send, we call 7% FEC, 12% FEC. So 7% of the bandwidth is used for FEC, or 12%. You pay, it's different algorithms, some are proprietary on the different vendors. But anyway, so the effect is there to correct. So how is it working? For example, I have a transceiver between side A and side B, I have transceiver using FEC. And between side C and side D, I have also FEC transceivers. In between B and C, it's regular, let's say 100 gig without FEC. And then I do a BERT test. What I am getting, I'm only getting 4-bit errors. Even though I had 3-bit errors, they are auto-corrected between side A and side B, and side C and side D. But in between, it's not corrected. Some people believe that if I get at side C with 4 bits, how come it's not corrected as it gets into the other? It's because FEC cannot correct something it doesn't have a reference to. It's always in and out. So it's always between two transceivers you can auto-correct errors, not from side A to side D, for example. There's always between one transceiver and another one. So there's no transmission of errors from their point of view, but if it's happening outside, it doesn't know it's a bit error. So it's transmitted, that's it. For him, it's a 0 or 1. It just blinks at 200 billion times per second, the laser, right? If you have 200 gig. Actually, if it's a 0 and a 1, it blinks 200 for 400 gig, yeah. Actually, it doesn't blink quite exactly. It actually fluctuates. But 200 billion times, yeah, per second. That's quite a lot. So the laser is quite demanding, and also the receiver. Now the RS FEC, like I said before, there's different coding overhead, and you have also the, if you look in the middle, the net gain. That's what you're looking for. A 9 dB gain at 100 gig, it's quite a lot. It's quite cool. So you can say, okay, I gain 9 dB. So if you know optics, which actually gives you 0.35 dB loss per kilometers, how much 9 dB gives you a fiber distance? 20, 40 kilometers? Yeah, something like that. Now, yep, 5 minutes, 10 minutes, 5, okay. Bandwidth limitation by dispersion. So when I said dispersion, you have chromatic dispersion and polarization mode dispersion. What is dispersion? I'll talk about it, but those chromatic dispersion is when you build the fiber, it's intrinsic to the fiber, that's what it is. You have that kind of, we call it CD, that's attached to that kind of fiber. PMD varies with temperature, with wind, with vibration. So let's look at it. So chromatic dispersion, you have two, I'll do it again. You have two pulses. They are traveling over the fiber, and they are reducing in power, of course, but they're also spreading. What's happening between the two pulses? They are overlapping, so the signal, the noise is raised, so the signal-to-noise ratio is impacted. Why this is happening? Because in the fiber, unfortunately, it's not totally symmetrical. It can be varying, quite slightly variation in the core size, making some wavelength traveling faster than others. For example, 1310 will fly not as fast as 1314 nanometers. So that's chromatic dispersion. Did I pass one? Yeah, no. Okay. So you have zero dispersion fiber. You can buy them. There's all kind. There's non-zero dispersion. You have 1310. You see at zero, you buy that fiber. If your dispersion, you want to have zero dispersion at exactly 1310, then you buy the non-zero dispersion. If you are into the DWDM world, then you buy the dispersion shifted G.653. Then this one has zero dispersion at 1550. So those are different ones. If you understand dispersion, you want to control. Chromatic dispersion can be controlled. Now, CD per type, so this different ones, but in general, you want to have no more than 15 picosecond per nanometer dispersion. I won't get too much in the details, but this can be measured. It has to be measured. Every time you're deploying DWDM over long distance, you need to measure CD, you need to measure PMD, because otherwise you can have major impact on the 100 gig or 400 gig transmission. It won't pass. It will have errors all the time, and it will happen randomly. So CD can be compensated. So you can buy CD compensator because it's a fiber, it's glass. So you can create one glass that will have 10 picosecond correction up to 10,000 picosecond correction. And then you put that in line, and then it autocorrects your CD. So CD, fine, no problem. But let's talk about polarization dispersion. You remember the light is polarized, and let's say in 2 dimensions to make it easy. And then so pulses can travel correctly if the tube is fine, but if it's not, if it vibrates, or if it's, let's say, not quite, I know it's an exaggeration, but so one axis will travel faster than the other axis. Now, if I take a fiber and I shake it like this is dispersion. Okay, same thing. So the dispersion, it will be affected by wind, change of temperature, any mechanical vibration will change the PMD. We call it PMD. And the PMD is the quality of your network. And when you do the measurements, it has to be windy, bad day, it's raining, perfect. So you're doing your PMD tests for long distance, and you make sure that it is within limits. For example, 9 picosecond, 10 gig, it's okay. For 2.3 picosecond for 100 gig. So there's a difference. So when you're looking at it, I know it's a simple measurement. It's picosecond because it's really, we're talking about speed of light here. So the picosecond may change. So when you look at the dispersion, similar to chromatic dispersion, but look at the bottom axis. Instead of having 2 different lambdas traveling at different speed, on top it's the same lambda, but what's happening is there's a dispersion within its own signal because of linearity or nonlinear effect. So making it delay accumulation. So let's say we have these cars starting, patch cord splice will not impact PMD, by the way. But roll condition will, whoops, sorry, I missed my nice old animation that we are keeping. Yes, yeah. And then we have this. Now, PMD can be measured. You can have, device that will tell you which portion of your fiber has the most. You see the big up red line? This is the portion of your fiber which is adding the most to the PMD. So instead of changing that 20 kilometers, you just have to change that 500 meters and you're fixing your PMD. So those are really important tools to use to understand what is the PMD on your network. CD compensation, I'll talk about that. There's no compensation for PMD. You have to replace the fiber, period. That's it, that's all. This is actually polarization. This is the DPQPSK eye diagram that is part of our guide that I'll send you to explain that. And really to finalize, it's a final slide. Signal to noise matter, it's not magic. And remember, 20 dB, 24 dB is the goal. So when you're doing optical signal-to-noise ratio measurement, 20 dB, 25 dB is what you're looking for. And do you have any questions? Sorry, it was rough after lunch, I know. I hope it was informative. If you need more information, let us know. And, or let me know, and I'll be more than happy to answer.
All right, thank you very much. We have one?
Maybe?
One more question.
Yeah.
Hey, this is Oliver from Uber. I know today, like with ZR, ZR plus, heat and power on the, powering that optic is kind of the big constraint. I know like OSFP is a little better at heat, but is there like a fundamental limit we'll get to at some point where you just can't cool a whole like line card of those optics, or are optics going to continue to get better? And
yeah, it's a good question. In fact, it's how do you cool down, let's say, 8 400 ZR plus. Mm-hmm. So it's a matter of space. Some manufacturers will provide you with a big rack, with a lot of heat dissipation, but you lose space. So it's a trade-off. I saw 4 ZR plus on a card and, 20 400 gig client. But that's a trade-off. Yes, you have to make sure that when you're buying these type of device, or if you're selling them, that you are controlling the heat dissipation of these 400 ZR. Yes, and 800 gig is even worse. Yeah.
Cool. Thank you.
Yeah.
Great. Thank you very much. I learned a lot from that presentation. Thank you very much.
Thank you.